number density would fall as e to the minus m over t. So as the temperature gets lower and lower below them, the protons and antiprotons annihilate, and their number density becomes exponentially small. Eventually they decouple from the photons. The universe cools enough and becomes dilute enough that there aren't enough photons to keep the system in equilibrium. But by that time, you would discover, and you might do that calculation later, I might put this homework problem. By that point, you would find that the number of protons, the number of baryons, would be something like 10 to the minus 20. But that's actually not the case. It's more like 10 to the minus 10. And why is that the case? Well, it's not the case because there's a baryon. If you think about baryon number in this case as being the relevant charge, there is a baryon asymmetry in the universe. That is to say, an excess of baryons over antibaryons, an excess of matter over antimatter. And what caused that excess is an interesting subject of discussion, something that might have happened in the first fraction of a second, or could even be in principle something that was true immediately coming out of the Big Bang. There's lots of different speculations as to exactly what caused the asymmetry. But once it set in and the temperature reached low enough, then essentially what happened is the number of protons and the number of antiprotons, or the amount of matter and antimatter, had a slight difference in their number. So compared to the total number of protons and antiprotons that were there at high temperatures, when you go to temperatures well above their mass, there were lots of protons and antiprotons. There was a tiny, tiny difference between the number of protons and antiprotons. As the universe cooled, what happened is that the interaction of protons and antiprotons going to photons, as it fell below their mass, then the protons and antiprotons could annihilate into photons, but those photons would be redshifted, and there wouldn't be enough high energy protons to do the inverse process. So that's to say, the protons delivered all their energy through annihilation into photons. So whereas before there was a huge sea of protons and antiprotons with a small difference, I could put it this way, a huge sea of protons and antiprotons, but with a tiny difference. What happened over time is the annihilation reached the point that the only ones left were essentially just the excess of protons over antiprotons, which was tiny, this 10 to the minus 10 figure. In terms of our thermodynamic equations, the way we would think about it is we'd say, well, the number of protons minus the number of antiprotons was going to be given, so when we get to temperatures well below the mass of the protons, would be given by that formula that we wrote down. There's a factor of 2 because there are the 2 degrees of freedom for the protons, the fermions have 2 degrees of freedom, and we just have e to the minus right now, you notice I'm setting k also equal to 1, Boltzmann constant equal to 1. Every time we can set a constant equal to 1, we'll try to do that. And so, if there were no chemical potential here, then to leading order, these two would cancel. You'd have to go do a more exact expression to work out that number. But with the chemical potential, and using the fact that mu p bar has to be equal to minus mu p, what we find is that this expression over here is approximately, I guess it's a sinh of mu p sinh of mu p over t. So instead of canceling, you get a residual amount, and that chemical potential is what determines that number. Or that number determines the chemical potential, whichever way you want to think about it. Okay? That's just an example. So wherever you have a charge asymmetry, there's a similar asymmetry that occurs for leptons in the universe. There's a slight excess of leptons over antileptons. The same sort of thing holds. There's some sort of chemical potential for leptons as well. Okay. So again, through most of the evolution of the universe, the thermodynamics of the universe is sort of simple, boring, solved by these equations. Okay, so it's perfectly solvable. But there are periods where interesting things happen. And that's the periods we're going to be talking about through the rest of the course. Some of them we'll start with things which are kind of mild changes in the universe, and we'll progress to more dramatic ones. Some of these involve deviations from adiabaticity that occur over short intervals of time. But those deviations from adiabaticity or simple behavior are the most interesting periods in the history of cosmology. That's where, things change, including dramatic ones, like the whole overall structure of the universe. So we'll begin with something mild, and then we'll work our way to things which are less mild. So, interesting events. We'll first of all talk about the case of E plus E minus annihilation. Two photons. When the temperature was large compared to the mass of the electrons and photons were in thermal equilibrium. This is a thermal equilibrium process. We'll estimate when it goes out of equilibrium in just a moment. It's an electromagnetic interaction, so it's not like the weak interactions we were talking about before. And so because this process was in good thermal equilibrium, you would expect that the temperature of the electrons was equal to the temperature of the photons. That's correct. They would be at the same temperature. But the number of degrees of freedom of the electrons, and if we're going to include the neutrinos, we could throw the neutrinos into it as well. Neutrinos are also in thermal equilibrium. Even though they're all at the same temperature, so with the neutrinos in there, we get to high enough temperatures. Even though they're all in thermal equilibrium, the number of degrees of freedom of electrons and neutrinos is greater than the number of degrees of freedom of the photons. There's 2 degrees of freedom here, there's 2 for the electrons, there's additional ones for the neutrinos. So actually, the dominant contribution to the thermal distribution of particles in the universe during that stage is dominantly due to the leptons, not due to photons. So this is sometimes called the age of leptons. It still will be called radiation dominated. In the sense that the energy density is going as t to the fourth, as you would expect in a radiation-dominated universe. But when you think about radiation, usually what comes to mind is photons. Radiation simply means kinetic energy plus any particles which are relativistic. The kinetic energy of any particles, and in particular the kinetic energy of particles that are relativistic. And if the dominant contribution to the energy density is due to any degree of freedom which is highly relativistic, whether it's a massive degree of freedom or a massless degree of freedom, rho is going to go as t to the fourth, and we call that radiation dominated. But formally, more specifically, more precisely, it's really the dominant source of energy at this time is due to the leptons. Until such point that the temperature is going to fall below the mass of let's say the electrons. In which case now, due to the Boltzmann factor, now they're going to become suppressed, like e to the minus m over t. Let's estimate what the collision time is compared to the Hubble time for this interaction. So we're going to use the usual story, 1 upon n sigma v for the collision time, and we want to compare that to 1 upon t squared. So in this case, the dominant source of scattering